All right, today we are going deep, right under the hood of Arista's EOS. You know, it's one of the most resilient network operating systems out there for a reason. We're going to find out exactly what makes its design so elegant and so incredibly stable. Let's get into it. It all really boils down to one massive question, a question every network architect has to face. How in the world do you build a network that just never fails? I mean, think about it. With today's giant data centers and constant change, how do you possibly manage all that complexity and still guarantee rock-solid stability?
Well, Arista's answer is actually, believe it or not, beautiful in its simplicity. Instead of having hundreds of processes talking to each other in some chaotic mess, they built a system around a central brain. They call it SysDB. Everything, and I mean everything, communicates through this one central hub. It's the single source of truth, and its only job is to tell all the other specialized parts what's going on.
To really wrap your head around this, we're going to use a metaphor for this whole explainer, and it's a really powerful one. Just think of EOS as the network's nervous system, right? SysDB is the brain, and all the other little programs are the specialized parts of the body, the eyes, the hands, the reflexes that go out and actually do all the work. So, how does this digital brain even come to life? Where does it start? Let's take a look at how EOS boots up and actually builds this single source of truth right from scratch. Now, what's so cool about this is that this super advanced system is built on something incredibly familiar and stable, Linux. See, EOS doesn't waste time reinventing the wheel. It lets a standard, battle-tested Linux distribution handle all the basic stuff, managing the hardware, the memory, the users, so it can focus all its energy on the really hard, high-level networking jobs. It's just smart engineering. And here's how the whole thing wakes up. It's a really logical, step-by-step process. First, the hardware does its basic power-on self-test. Then Arista's own bootloader, which they call A-boot, kicks in. Its job is to find and load the main EOS operating system from storage, which then fires up the Linux kernel. And then, here's the magic moment. The SysDB database is created in memory, and suddenly all those specialized agent processes pop into existence, ready to get to work. Okay, so let's get really clear on what this brain is. SysDB is basically a system-wide database. It is the one and only source of truth for literally everything happening on that switch. And when I say everything, I mean it. From the configuration you just typed in to all the complex routing tables, right down to the temperature of the physical chips on the circuit board. If it's happening, SysDB knows about it. This simple phrase, this just perfectly captures the entire philosophy. It's the perfect division of labor. The brain, SysD, its job is to know the state of the world. That's it. And the hundreds of other processes, the agents, they're the specialists that actually go out and do the work based on that state. So why bother designing it this way? Well, the payoff is huge. This is where you see the genius. For starters, resilience. An agent can crash, restart, and boom, it instantly gets the current state from SysDB. It doesn't have to replay a long history of events. It's just back in the game. What if an agent gets totally overwhelmed? SysDB protects it. It just holds on to the updates and only sends the absolute latest one when the agent is ready. It even validates data, so you can't have an agent trying to set a link status to 42. And it's super efficient, because agents just subscribe to the topics they care about, and that's the only information they get. This is the secret sauce to its stability. And these agents, who are they? Well, they're the expert teams in our nervous system. We're talking hundreds of small, totally independent programs, and each one has exactly one very specific job. You've got an agent for the BGP routing protocol. You've got another one for LACP to bundle links together. You've even got tiny little agents whose entire life purpose is to control the fans and read temperature sensors. Specialists, every one of them. All right, theory is great, but let's see this thing in action. We've met all the players. Now let's watch how they work together as this perfectly coordinated system. We're going to trace one single simple event and watch this nervous system light up. So here's our scenario. Something that happens every single day in a data center. Someone unplugs a network cable, a link down event. We're going to follow that little piece of information as it zips through the entire system. Okay, now watch how elegant this is. First, the hardware, the senses of our system, detects that physical connection is gone. It sends an interrupt signal. A specialist, the forwarding agent, gets that signal and knows exactly what it means. Link is down. It does only one thing. It tells the brain. It updates the state for that interface to link down in SysDib. SysDib then instantly publishes this news flash to every other agent that cares about interface status. Immediately, the LACP agent sees the update and yanks that link out of its bundle. At the exact same time, the LED agent sees it and changes the physical light on the port from green to off. It's a perfectly coordinated, instantaneous response. But here's the really brilliant part. Think about what didn't happen. The forwarding agent had no idea the LACP agent even existed. They didn't talk to each other. They didn't coordinate. That would be pure chaos. Instead, they all just listened to that single source of truth, the brain, and knew exactly what they had to do. So let's zoom back out for a second. Now that we've seen the mechanics, the nitty-gritty, let's connect this design to the real world and talk about why this state-sharing model is just so incredibly powerful. To really get it, we've got to touch on a fundamental networking concept, the control plane versus the data plane. The control plane, that's all the brain's work. It's the thinking, the decision-making done by the EOS agents, like figuring out the best path for your data to travel. The data plane, on the other hand, that's the reflexes. That's the specialized hardware, the ASICs, that just forward packets at lightning speed based on the decisions the brain has already made. You see, EOS is the intelligence that programs those super-fast reflexes. And here it is, the whole picture, all the pieces fitting together. You've got the raw hardware at the bottom protected by that sturdy Linux kernel, and sitting on top is this beautiful symphony of specialized agents and drivers, all perfectly orchestrated by SysDib, our central brain. So, what's the real takeaway for you? Why should you care about this design? Well, first, way higher uptime. An agent for one little protocol can crash or even be upgraded while the system is live, and it won't affect anything else. It's wild. Second, you get faster innovation. Arista can add a totally new feature just by writing a new, self-contained agent without ever touching or risking the stable core of the OS. And third, you get this amazing visibility. When you have one database that holds the entire state of the system, trying to monitor, troubleshoot, and automate your network becomes 1,000 times easier. Ultimately, it really all comes down to this. This state-sharing architecture we've been talking about isn't just some feature on a datasheet. It is the absolute foundation of EOS's famous stability and its incredible power. And that kind of leaves us with one last question to chew on. This model, this idea of a central state database with small, specialized stateless agents, is such a powerful pattern for building complex and resilient systems. So, if software can orchestrate a network this elegantly, just think about where else this model could apply. Thanks for joining me.